Hello, everyone. Welcome to another seminar of the Astronomy Department cycle of seminars. Many thanks for being here with us in the Google Meet. To have Professor Cristina Chiappini with us presenting work. Many thanks, Professor. Okay. Tenho. Tá. Quando você fala. Tá. Não sei que. Deu um problema aí na conexão, né?
É. Só começar de novo, Maria. Você pode começar.
Assim você falar, eu... Tá, tudo bem. Ótimo. Hello, everyone. Welcome to another seminar of the Astronomy Department cycle of seminars. Many thanks for joining us today here in the Google Meet, or if you are following through our YouTube channel. We are very pleased to have Professor Cristina Chiappini today presenting her work. So many thanks, Cristina, for accepting the invitation and being here sharing with us. So many of you already know Cristina, but for those who doesn't know her, she received her PhD here at the IAG, and she was a postdoc at Columbia University, and later she get a permanent position at the Trieste Observatory. Then she moved to the University of Geneva, where she was my trained assistant, and from there to a permanent position at the IAG-Institut in Potsdam. And her main interests are chemical evolution of galaxies, asteroseismology for galactic archaeology, spectroscopic surveys, chemodynamical models, and more specifically, the galactic bulge and the metal-poor environments. And today, Professor Chiappini is going to talk about galactic archaeology with high precision data. So as always, I will ask everyone during the talk to turn off your microphones and your cameras. And if you have a question, raise your hand here, or you can write it down in the YouTube chat. And the questions will be asked after the presentation, like always. So, Professor, whenever you are ready, you can start.
Okay. I'll just share. Hello, thank you very much for the invitation. Let me just see if you are seeing my cursor. You see my cursor? Yeah, okay. So I thank you very much for the invitation. As you know, I have a strong connection to IAG, where I did my PhD, where I did my university in São Paulo. So I'm very happy to be here today. Today I'm going to present, give you a general view about galactic archaeology now that we have so beautiful data and also very high precision data. It's vague what this means, but you'll see in a while. As you see in the starting of my presentation, I have put a map of the galaxy. You understand soon. This is how we would see our galaxy if we were outside the galaxy, so seen from above. And here are the many missions that I am using, or that I am from the data that I'm using, and you'll see along the talk how you combine all this data and the beautiful things that you can achieve. So, of course, this is a work by a group. We never work alone, and I have great collaborators. Some of them are listed here. But I also wanted to say, and not miss this opportunity to thank a lot the beginning of my career and the sponsor by FAPESP, CNPq, and CAPES, and how important is that these support agencies have funds is clear to me and should be to everybody. So, galactic archaeology is the title of my talk. What does it mean? So what do we mean by galactic archaeology? We mean trying to reconstruct the galaxy's history, from the present day that we see the kinematics of the stars, the movements of the stars, and the chemical information of the stars. Chemistry is especially interesting because it gives you also information on the past, because the amount of chemical elements in the stars change as a function of the history of the galaxy. But once a star is formed at a certain point from the gas, this composition is preserved in most of the stars. So it gives you an idea of what was happening at the time of the formation of the star. So why is this challenging, even though we have so much data? So there are many challenges here because we have in the galaxy a mix of populations with very large overlaps in parameter space. So they overlap in velocities, in metallicities, and ages. And so if you say, I want to study the thick disk or the thin disk or the bulge, you have to always say how you want to select this. And if you select by the chemical only, you may be having bias. If you go for kinematics only, you may have bias. So it's a very complex thing. Another complexity that's very important is that stars move away from their birthplace. So a star is born in a place and it can migrate to another place. And this is now clear. The process can be many to make this happen. Therefore, they are very difficult to model. There are many sources for this migration. Some stars migrating on the disk, you will not see, for example, any hint from their eccentricities or so. They will not be hotter. They will be just in circular orbits like those that were born in that particular radius. And the only maybe thing you're going to see is a difference in chemistry. And you will figure out that these stars are migrators. So another difficulty has been that we, for many years, were confined to small volume around us, around the sun. So I had a look in my last seminar at the IAG, was in 2012, and I looked at these two transparencies I presented at that time. And at that time, I was using data that was coming from Hipparcos with high spectroscopy follow-up by several groups. And these two transparencies that I'm putting here, I was comparing some tracks for chemical evolution models for thick and thin disks with the very good data to try to constrain the stellar yields. However, there were at that point already in 2008, 2009, things that were complicating the scenario, which was, for example, you could see here in some of these abundance plots, you would see that these very high metallicity stars, they didn't fit actually into the scenario of the evolution of the solar vicinity. You also had some data and for this paper from Trevisan, Barbuy, and collaborators, which also have shown that the most metal-rich stars next to us, they were not the youngest, as you would expect in the normal simple chemical evolution view. So we had to go for a different way to interpret this and consider that you actually have radial migration, and maybe those stars, this is just the tip of the iceberg, but the stars are being moving around in the galaxy. And so when I spoke to you in 2012, I explained about a new way we thought of doing chemodynamics then, not only chemical evolution, a chemodynamic approach, and I explained to you this paper with Ivan Minchev and Marie Martig, which we call the MCM model. So today, since there, so 2012 to now, at that moment we were just writing that paper. Now we have the data. So today my focus is mainly on the data, but have in the background some ideas that we discussed already before. So the main brain of this data is this fact. The stars move around, especially in the thin disk. And if you have here the number of stars, for example, look into this diagram here, the number of stars, a function of metallicity at the solar vicinity, or stars collected between 7 and 9 in galactocenter distance and below 3 kiloparsecs from height from the midplane. So the stars that are around us, you have this metallicity distribution. But if you look so I'm looking in this now around the sun, but if you see where the burst rate of the stars are, they are spread in a very big region. And this that you see here, this is are the modeling where you see the burst rate. Of course, we don't have the burst rate of the stars, but this can be translated here when you have the metal distribution of the metallicity of the stars next to us. And you see that the green line here is what you expect for the stars born at the solar vicinity or at the solar circle. But you see an excess of high metallicity stars. And according to our modeling, this was meaning that those stars was mainly born in the inner regions. And that's why they are more metal rich. And that's why they're not the youngest. They could be older, or like the data of Trevisan and other data also have shown. So this is just a model, right? And of course, we then can sit in any radius and then do the same predictions for different distance from the galactic center, as a function of radius and high and or below above the plane. So this was the status of what I discussed with you at that time. And I said we would like to be able to test these things, the impact of radial migration and all these particular things. So in between that time, 2012 and now, or some years before now, I summarized this in 3 important observational breakthroughs have happened. And they affect our capacity, the increase of a capacity of volume coverage of the galaxy, our capacity to have the ages, which are essential then to disentangle this mess that the galaxy went through, and very good distance, and for that you need extinctions. And these are the 3. So the 3, I call 3 revolution galactic archaeology. The first is asteroseismology of red giants. You understand soon what this means. And the opportunity that this asteroseismology gives us to obtain precise ages and distance for stars that are far away, because they are red giants, I can see them far away. Astrometry, of course, you all know the great impact that Gaia is having into the field, not only of galactic archaeology, but many fields, but as predicted and wanted in the Gaia, in the galactic field is enormous, the impact. And the third revolution is really apogee. There are several spectroscopic surveys, which are all very important, but apogee essentially opens a window, a spatial window in the galaxy, as you're going to see soon. So, astroseismology of red giants. So, what is astroseismology? It's just a time series where you measure the variability with very high quality and precision of the photometry of the star. And then you can estimate the modes that this star is varying, and you can, from that, transform this information into stellar ages and radius and mass, essentially, and then you have to convert into stellar ages. This field became very important once you knew, for galactic archaeology, once you also obtained asteroseismology from red giants, because you could see then the galaxy far away. And we had the people involved here had a lot of efforts to make that most of the astroseismic targets would be then followed up by surveys, so that we could combine the information of seismology plus spectroscopy and then make even more precise estimates of ages and distance. One example here of this impact, where you can obtain masses for a red giant of the order of 10% and a radius of 3%. This means that you can have distance with a precision of few percent and masses between 20 and 30%, doing, let's say, the standard seismology. And we discussed the impact that those ages can have into this paper. Here I'm just showing you 3 fields of 3 missions, Corot, Kepler, and K2. K2 is an extension of Kepler mission. After Kepler had the problem, it became K2, which is very nice because it has several line of sights. And then you see, for example, the distance you get from seismology and the distance you have, for example, for eclipse binary, and the agreement that you have and the precision that this can give to you. The other importance of red giants is that you have a very good, a more simple age-mass relation that is also plays a role in the way you're going to transform the mass into age. Of course, it's always model dependent. The Corot was the first mission that we used for that. It had at least two fields pointing in different directions of the galaxy towards the inner galaxy center and outer parts of the galaxy, and therefore it was a very important tool for first to address galactic archaeology, so the mapping of the disk of the galaxy. Soon after, you had K2 and Kepler. Kepler is pointing up, and K2 is pointing to several line of sights. And so through this line of sight, through these pencil beams, you could obtain very precise ages and distance, and mass and distance. Seismology of red giants then had major impact in galactic archaeology because it provided precise distance. We managed to organize a spectroscopic follow-up of the main surveys, and this also has an important point that it gives also a gravity and an order of magnitude more precise than the gravity that you can extract from spectroscopy alone. And this also, there are other ways to use the seismology that you can even improve and reach up to 10% precision in ages as well. And we have a recent result on that. But it also opened the possibility to get ages also for old field stars, which is also a very important thing, as you're going to see now. So with all this happening, we organized at IP, many of you came, Yahoo Symposium, where we discussed a lot the appearance of all these spectroscopic surveys, the role of seismology inside this, how we're going to organize ourselves to follow up these seismology targets with the surveys, and also how we get ready for the avalanche of data that Gaia would have. This is just before the Gaia year 2. It was very nice panels of discussion during this meeting. The second revolution then is really Gaia. Gaia DR1 had 3 releases for now, and we are in the EDR3 that happened just last December. But the big transformation, really we had to change the way we work, was when Gaia DR2 came, and in 2018. And of course, now the data is much more, is even more beautiful in EDR3, and we are also eager waiting for DR3. During this time, we reorganized our team, which we call Star Horse team, and we started. The first thing was in the hope to get this good map of the Milky Way, which is one of the goals of Gaia. You need complementary information to add to Gaia so that you can go and get distance and have an idea of extinction beyond the 1/parallax volume, where you can use the 1/parallax simply, which is just in a very close by volume. You wanted to extend that. And we have developed this Star Horse code, a spectrophotometric code that is able to use either only photometry plus Gaia information, or just photometry and spectroscopy and Gaia information. And here you see Friedrich Anders, who you know, probably, he was in Brazil. Ana Queiroz is also now my PhD student. And Arman is a colleague here at IP. And of course, part of our team is Basilio, but he's not in the 2020 picture. We are all isolated here, but still working together. So what we managed to do is, as soon as Gaia DR2 came out, we managed to do a map of the Milky Way by combining the Gaia data with photometric information first, down to G18, and was amazing to have the CMDs, as you show. I'm showing here some examples to you, which suddenly you have 265 million objects and so on. It was a very interesting and very intense work, where we estimated stellar parameters, we estimated distance, extinctions, but also temperature and other parameters for those stars, and made it public. And immediately what we saw of the advantage to combine the Gaia data with complementary information was that, for example, if you take this map that was published soon after by Bailey Jones of Gaia DR2, and then you do our use of extra information from extra photometry, you would see already that you could see already the galactic bar coming out, which is as in a density map like this, which is beautiful. This is Epsilon X. You're seeing the galaxy, let's say from above. We are here, and you see this concentration. When you look in the red giants, you see a concentration that indicating the bar in that region. Therefore, the Gaia simulated end of mission map was something like this, and we were very happy that just in 2019 we already had a map like this which is the map that comes out from this Star Horse run, which we made public also, all this data for everybody that would like to use, with the caveats that this has, because in the bulge, of course, using only photometry, you cannot gauge all the extinction effects, and therefore you have some shortcuts. But this is what we did as a first thing. Now you have a Gaia EDR3, you have paper with 1.47 billion stars with distance, and it uses our Star Horse as a way to see if they are doing well by using more information. And we are happy to see that, especially the paper then of Queiroz 2020, which I'm going to show you now. But by using the new Gaia EDR3 and complementary information, you see that now it also starts appearing in the Gaia group, this bar. The third revolution is Apogee. Why? Okay, the third breakthrough came with Apogee, and here we run a Star Horse now using the spectroscopic information and the Gaia information. So this was the first paper of Anna, for several spectroscopic surveys, so that you have a kind of homogeneous set made available as well, is all public. And what you see here is the edge-on view of the galaxy, and you see, for example, here in the bulge area, you see that essentially only Apogee is reaching there. And Apogee is also very important because it's finally giving you a view very close to the galactic midplane, which the other surveys, being not in the infrared, have this cone shape. So this is really opening the view we have to the main place in the galaxy where you have most of the stellar mass. So this is really impacting a lot, and it's the data we need to test the kind of models that I was talking before. This is the view, again, of all these spectroscopic catalogs for a total of 6 million objects. Most of them are LAMOS, low-resolution objects that go more to the northern part, but the inner because it's another hemisphere, you see more the outer part of the disk, and here the inner parts of the disk covered by Apogee. You can see essentially only Apogee is having data here. So this is a revolution. Okay, now I explain you what are the 3 revolutions that have happened and how hard we have worked on it since my last talk there. So the amazing thing now is the power that you get when you combine seismology, spectroscopy, photometry, and astrometry. It's essentially like you just now can ask and the data will tell you almost that. Of course, your question will require different precision in the data. And so you always have to have in mind that you can ask the question different ways, and then you can combine what you see in the big picture with what you see in the local and more high precision picture. So the things in the end have to tell the same story. So that's how we have been working. And now I'm gonna focus on a purple here of results for you that take advantage of this combination: good distance, good extinction, good ages, and so on. So as you see, the samples are going to change. The size of the samples are going to change depending on the question we are asking. So one important relation is the alpha over iron versus age. The alpha over iron versus iron plot, as we showed quickly before, but I'm going to show again with more calm, is essentially a plot that can be used as a cosmic clock. Essentially, when in the very early beginning of the things, when only type 2 supernova are contributing to the interstellar medium to enrich the interstellar medium, you have high alpha over iron. And when then it passes more time, you have a plateau, let's say, and then it passes time, the type 1a have time to contribute, this takes some time, and so this alpha over iron starts going down. Therefore, it has a relation with time and with age. So, we had the data from Hipparchus down to 100 parsec, and now you can see we can at least have a very precise data also up to 2 kiloparsecs from the sun. So this is the historical paper of Fuhrman with a very, very high precision data from Hipparchus at 25 parsecs is the volume. Now, where you see this, all the stars are here in the thick disk, and they are like thick disk stars. Then you have the thin disk, and you have some intermediate things here, with where he was able to determine age because he was using subgiants. and then you had this kind of two discrete things for thick and thin disk. At that time, we have translated that into this sort of diagram. Here you plotted the opposite, iron over an alpha versus an alpha element. The alpha, why not iron? Because the alpha is tracing the star formation. When the star formation, if the star formation stops, the alpha in the interstellar medium stop being released because it's made by type 2 supernova. So while you have only I could translate this into the plateau, and then the fact that you have this for the thin disk, and that we seem to see a gap in those diagrams, you could translate this in two main episodes of star formation, which at that time we call the twin-fold model. So this is a very local thing and a way to interpret this. So recently, you were able, by combining Apogee and Kepler data, to obtain ages for red giants with the mean precision of 25%. And finally, plot really alpha, age versus alpha over iron. And you see, what do you see here? You see some scatter, but some relation happening. But then you see a very coeval population once you have passed some value of alpha over iron. That's what the data is telling you. You see also some interesting outliers. Most of the data is here, but you see some outliers. These are the young alpha rich. They are known to us already in 2015. We, for example, here is what you would expect of a typical chemical evolution model, magnesium over iron versus age, or, for example, some other elements that behave as such. And then you have this forbidden region where you don't expect that high alpha stars be very young. And we found some of those. And these are probably, because these age are determined mainly by the seismology, right? So this in this case was Corot plus Apogee. You are using the mass to determine the age, but if there was any accretion event on this mass, then this mass is not anymore the original mass, and so your age will be wrong. That could be indicating mass accretion into those stars. There are several other papers in this subject afterwards. And we see them again. Here is again this more recent paper where we use Apogee and Kepler, so the ages are much more precise. And you have now the alpha over iron versus iron plot where you color by age. And these red points here are the young alpha rich stars. They are young. Or you can also see in the same way I was showing you before. And you see this very low scatter for this population, which is what we call the chemical thick disk. Okay. So what is this telling me? This is important. It is because this plot shows just the posterior probability distribution function of the age spread of this high alpha population that we just saw before, taking into account all the uncertainties. And this cumulative distribution shows that with 95% credible interval for showing that the intrinsic scattering, the age of the thick disk is below 1.25 gigayears. So this thick disk was formed, this chemical thick disk, so this high alpha population we see next to us was formed in a very short time. And this has consequence for the way we model the Milky Way. So, but is there a bimodality in age? And do we see a difference in age as we go far from the midplane of the galaxy? Yeah, we seem to see this. This is, again, what we see with our data, low alpha and high alpha, as a function of age. You see this depression here. Is this a discontinuity? Is not or not? We start being able to see, because now we have a precision of 25% in age. So you start being able to pick up these details in the evolution of the galaxy. You can also use K2 data instead of Kepler data, and we have used this in this other paper and analyzed these two fields of K2 that go, here is again the distance from the galactic midplane. So you have one going up, one going down, and here is, I'm showing you instead the Kepler field that we were discussing before. So what do we see in these two fields in terms of age? So in the K2, we had one sample without spectroscopy. So in that case, we just got an age, of course, much more uncertain. And we paired the sample in close to the plane, above the plane, and you see this dichotomy. So above the plane in magenta, close to the plane in green, you see this dichotomy in age. And if you take the full thing, you see this double peak. Here is, if you have a spectroscopy, then you can cut your sample in high alpha and low alpha. And again, you see what you just saw also for the Kepler data. The high alpha has essentially old ages, and the low alpha has younger ages. Is there a bimodality then that accompanies this bimodality in age? Is there something else in the kinematics? This has been a lot of discussion. This is still discussed, but if we take this sample with such precision, we start seeing that if we take as a function of age the stars, the stellar velocity dispersion in the z direction, you see that you seem to have a jump. Now, of course, such that the thick disk stars, this component is very, the chemical thick disk stars is very hot. Is sigma z much larger than what you is not a linear increase. That's what we discussed. So this result seems to indicate that the thick and the thin disk are in fact discrete populations, and this is start to be seen more clearly now with good ages. So the chemical bimodality is real and could be related to the health of star formation. The chemical thick disk is a coeval population, and this suggests that the thick disk was not an effect of radial migration. The thick disk was most probably an ab initio fast component formation, as some also cosmological simulation seems to suggest. Now, do we see migrated stars? I started my talk saying that we see these migrating stars around. Do we see this in this larger volume? So here is what in the Hipparcos volume was done with in 100 parsecs with uncertain age, but very important work showing, again, as we discussed before, that the most metal-rich stars did not seem to be the youngest. They are actually intermediate old stars here in this volume of 100 parsec. Okay, so now you are able to look to this into a 1 kiloparsec around us, and with the same data I show you before, Kepler plus apogee, and indeed with ages of 25% uncertainty, we are able to see that in fact once you have gone to metallicities above 0.25 in iron, you really get not anymore the most youngest stars, but essentially you get a broader age range there, which is a signature of radial migration. Asteroseismology then can also have an impact in constraining the earliest phase of the galaxy, so the metal-poor environment. So, for example, when you are in the metal-poor environment, it's very difficult to get ages. You can use, in principle, this nucleochronometry to get ages if you have thorium and uranium lines, but you need the star to be very enriched in and capture elements, and this is a very rare situation, and you need very high signal to noise, very high resolution, and you can do only very bright stars. And these objects are then rare, about 1 million stars in the solar neighborhood, not applicable to larger samples. So we did a pilot program using rave stars that we identified in rave as being metal poor, and but they were also in rave and K2. And then we got UVS data for those stars, and then showed that it was possible to obtain reasonable masses for even in this metallicity range. Look how metal poor I am. I'm below 0.6 in Fe over H, going down to minus 2.6. And here in white was previous data where people tried to do this, but there were some developments, and we can show, before it was very weird because the masses of halo stars being above 1, it was not expected. And in fact, now you have a more consistent masses for the metal poor stars, which translate in ages that are older, probably more intermediate here. So we have now shown that this is possible with this pilot program, and have applied for ESO, for more UVS data for a larger sample of metal poor stars, and we got many are getting the data right now. So this would be a very nice window to study a metal poor environment with age. We can push the age to even larger precisions, and this is done recently. This is done recently by using a different way to treat the seismology. individual oscillations instead of using just the two more simple parameters, which are delta nu and max. I'm not going to enter into the details. But what is important, and we have been able to use this in one specific case, because the Kepler is a very, very precise data. It allows for very precise asteroseismology. As you know, one of the main discoveries after Gaia came was the discovery of Enceladus, that our galaxy had a big impact with a galaxy that was also big in the very beginning of its evolution. No? This is the paper by Amina Helm in Nature. This is a simulation of what she would expect for these velocity plots. And this is, in the simulation, the counter-rotating population that she's seen the data, and that is exactly what you expect if you have a merger galaxy with us. She identified these stars using apogee data here. They are metal poor, and if they are put more or less on a track, they are essentially, looks like they are old. They are retrograde objects, and this has been called as the Enceladus galaxy. This was also seen in the color magnitude diagram, where we have these two. When you go for the, let's say, metal poor halo, you see these true sequences, and Carmen Galar has also tried to estimate the ages using CMD and show that this blue is essentially, the blue sequence is essentially the accreted debris of that event, and this is the in place how the galaxy was at that time, or the oldest alpha population in the galaxy by the time we were hit. More recently, we then studied some of these stars that are low magnesium over iron at metal poor range, but have large eccentricity, so good candidates for being part of Enceladus. Forget about this plot about the moment. And then, if you plot those stars in this diagram, this Gaia diagram I showed before, we didn't select it like that. We selected based only on chemistry and eccentricities. And if you plot here, you see these two sequences here. And of course, we are using seismology, so we are in the clump and the red giant branch. We see that those stars take more or less different places here. So this one, which is essentially the high alpha population that is in the galaxy that we don't think was accreted, and this is the accreted population. Here, the difference is that now for these stars, we are able to obtain an 11% precision in age, which is really amazing. And if you now look to these two populations, just the A and C, which is like the accreted and the one that was in place, you see a small difference in age, such that the accreted population is a little bit younger than the one that was already in the galaxy. Look, the kind of precision you need to disentangle these events that are happening very early in the formation of the Milky Way. And this has consequence, and has consequence for the way we think the Milky Way was formed. So the Milky Way had already in place an important component, very old and very alpha rich by the time we were hit. Now let's just use the last minutes of this talk to leave the solar vicinity. Everything I show you for now was around us using very precise data. Around us, meaning around 1-2 kiloparsecs from most of the data. Now, let's see what we see then in the disk using this data, increasing our map now. So, are the stars migrating that we saw in the Hipparcos volume, that you saw in the 1 to 2 kiloparsec? Do we see them in the outer disk? Here we have shown using Corot and apogee data, was a part of the thesis of Friedrich. Now you have the alpha over iron versus iron data for two different beings of guiding radii. The outer being 11 to 14 and 6 to 7, and now each point is colored by its age according to the Corot apogee data, and blue being young, red being old, and yellow being intermediate. Look here, you see, for example, in this outer region, which is where I want to focus now, you see these intermediate stars being metal rich, and this is a chemical evolution curve colored by the same age as the points, so old stars, then intermediate, then young. And so it more or less coincides with where we find these blue points, but this you would not expect. So these, we think, are stars that have migrated from the inner regions. Does this impact the observed metallistic gradients in the galaxy? Yes, it does. So here we have used those 600 Corot stars, so Corot plus apogee, for which we have this 4% area in radius, 9% in mass, and again 25%, which translates in 25% in precision in age. But now we can leave the solar vicinity and we can look at the famous gradient we have in the galaxy, iron versus galactocentric distance, here traced by other traces, younger traces, and overplot are the Corot stars, the younger, the 1 giga-year Corot stars. So to show that essentially you are as tracing the same gradient as younger populations, but now because you have the age, you can break the observations into different age beams, and you see that here's again metallicity versus galactocentric distance for different beings of age, and you see that as you go old, you see a larger scatter in the ages. And we had used our MCM simulation, so our model, the one I told you before, which is these little particles, and this is also a chemical evolution model, is the curve. You see that the prediction of chemical evolution model in the beginning, the MCM say for very young stars you have a small migration, so the points of the MCM simulation are almost above the gradient of input gradient we gave. But as you go older, the stars have more time to migrate, so you would flatten. And now what Friedrich did, he prepared a mock catalog, how you would see this model of the galaxy if you have look just like the data of Corot look, and this is our mock. So you see that this kind of radial migration situation predicts that you have a flatter gradient in the past. But of course, here we are still confined to 6 to 15 kiloparsecs. It's very important to extend this to other regions. Now, this has also implication for open clusters. When you observe open clusters, here I'm showing you the Ocaso survey paper by Casamiquela. Again, the metallicity versus radius compared to the chemical evolution model and to the MCE, so our Minshev et al. Chemodynamical model. And here I plot the same age, the models and the clusters that have this age. Look that these models were made before these clusters, okay? So we are not tweaking the models to fit this data. And this is what you would expect from 1 to 3 giga-years and then older data. What you see is that the points, they displace from the curve. They get displaced from the curve more or less like the points into the chemical dynamical model. So this shows that you can have at the same galactocentric distance open cluster that is older than another one that is, more metal rich, although it's older than a more young cluster at the same galactocentric distance. This also is a way to the way to explain this is also radial migration, that these clusters have migrated. More recently, this has also been compared with in this paper by John Donner using apogee data. Again, same plot, iron, galactocentric distance, the plots of the clusters of apogee, and how, as you go with age, they disperse from the chemical evolution curve. So this, to me, is showing that the impact of radial migration into the disk. Now, what about the alpha over iron bimodality extending to other regions? This is also a very important thing. Since the beginning of apogee, we start having these maps of, here again, I'm now showing alpha over iron versus iron plots. But now here, the bottom curve, we are at very close to the galactic plane. And as we go up with each line, we are going more and more up into the galactic, above the galactic plane. So 1 to 2 kiloparsecs above, 0.5 to 1, and 0 to 0.5. First of all, below 1 kiloparsec, or this being especially 0 to 0.5, this is really coming out just because of apogee. Now here, because you could not see very close to the plane, as I said before, and here is from 0 to 2 kiloparsecs from the galactic center, going out to 10 to 12. And in the paper, we have a second figure that go up to 20 kiloparsecs. And what you see that this alpha over iron versus iron diagram varies. There is a map, there is information here, right? So first, we were sitting here, essentially, right? And we see this thing, and we had the impression with the first data of apogee that we had one sequence coming here after. but look instead, the double sequence is happening and is very clear as you go to the inner parts of the galaxy. And then as you go to the outer parts, you have essentially a one sequence, and this is only the low alphas are shown there. Above here, it shows the kind of precision we manage with StarHorse when we combine the apogee data with the Gaia data. And it's amazing that you have something like 10% precision in the inner galaxies. In magenta is the precision in distance, and in green is the precision in extinction. So, well, that has opened also a lot of things towards the bulge. So we wrote, me and Beatriz wrote together with myself and Ortwin, the chemodynamical history of the galactic bulge, where we made a review of everything we knew about the bulge just before Gaia DR2 and Apogee DR16. Essentially, after this data came, you had a traffic jam of work in the bulge, which with the complication that you in the bulge have extinction, so it's like a traffic jam in the snow. And this is a bulge boom number of papers, which of course I'm not going to present to you, but it's very interesting, and I think you should invite people to talk about these things. But I just want to give you a vision of what we have shown in the paper, the second paper of Anna. For example, this is the X and Y view now with apogee. So this is all spectra, high resolution, for which you have information for more than 15 chemical elements. So you have a lot to do still here, right? And people are doing, of course. Here is, if you see the galaxy in Z versus radius, and you see that you still lack some data in the very inner parts. But here I'm not showing you the DR17 data, where is even more improved coverage that we have now. And this is our maps of extinction. You see how high the extinction is here. And that's why in this region, we cannot really get through very much when you are very much close here. And we lack then data here, as you see above. You zoom to that region and you see this beautiful pattern here, this beautiful bimodality, but also you seem to see a gap in between the two things. And there is a lot going on to interpret this sort of thing. But what interested me is that how can we push to the data to then go to provide the constraints for all kinds of things that we are trying to understand. We go one step further and are able to define a proper motion selection function, a sample that gives you even more confidence that you are really inside the bulge. And thanks to Gaia EDR3 now, where we are already using the proper motions, which are a factor of 2 to 3 improved with respect to Gaia DR2, which was already amazing. And now you see this beautiful thing here in the bulge. We go beyond that. We take the sample and compute the orbits of this sample with the help of Angeles, and then study the sample in a Z-max eccentricity orbital windows. Why? Because you are in a complex galaxy now. The components are not able to, you cannot detach the thin disk, the thick disk, the bulge. So any kind of decision to cut in chemistry, cut in kinematics is dangerous. So what you do, you study, this is all data in the inner 2 kiloparsecs, and you study this, how in these windows, the data is transforming from more thick disk-like to thin disk-like to bulge. And this gives you an amazing view of also the bar. And that's what we do in this second paper. So I spark your curiosity for the second paper. I think you should invite Anna. I don't want to spoil these results. But this data that I show you in this talk are giving a lot of discussion, because the Milky Way is sparking debates on how galaxies form, how the simulations can be made, how to compare with the simulations and the data of the galaxy, age gradients in a geometric thick disk. I always talk about chemical thick disk, because we think we see the thick disk in the outer parts essentially made by this young population. So many questions are coming. I just put some papers here for you, but it's very hard nowadays to really do a complete cover of this, because there's a very rich moment of discussions. So how about the future? We have many ideas now how to use this data, but we also have clearly where we still lack data. And for that, we have foremost is this multi-object spectrograph that will be in the VISTA telescope. It's a project that IP is PI, and which I am, together with Ivan Minshev, PI of the formidable low-resolution survey, which is the part of foremost that you look in the disk here. And that's what we hope to increase the coverage of the galaxy, to complement the data from Gaia with more spectra. Low resolution, okay, is a lower resolution, and we have there will be also survey high resolution, which is more confined, but this will be a really discover machine when you put this spectra together with all the information we will have. So this, we just submitted the ESO GTO proposals in December last year, and we are actively working into the future of the galactic archaeology of the Milky Way. I leave you my summary. Essentially, I just want to say that the distance that we have computed, they are all public. We're made public, the 200 million, but also all the 6 million stars from also spectroscopy. If you want to take a message from here, I think it's very important to say that the precise ages haven't showed that the spread in the age of the thick disk is very small. The precise age have confirmed the migrators are in the local volume, but also in the full disk, and that the very precise age, really 10% ages, are able to open a new window in the way we're going to study the earliest phase of the galaxy formation that was not quite, it was very, very busy. Okay, I thank you very much for the attention.
Okay, thank you. Thank you very much, Cristina, for this talk. Okay, if anybody have questions, please raise your hand. I have a question concerning this Enceladus collision with the Milky Way. Mm-hmm. Is this a complete merger, or there is some rest of this galaxy out there?
Rest of this, no, this is a merger that has happened 10 giga-years ago.
It was, so you want this, it was a complete merger, let's say.
Yeah, I mean, now, in this sense, it's a complete merger, okay? It took many giga-years to merge. In the volume we are searching, there is now surveys going even further away, and you still see this debris of Enceladus. But mm-hmm. You don't have only Enceladus, you also have other things that merge as well. They were already found. And you can study them also using energy, angular momentum, all the information you have, yes. Again, from Gaia plus chemistry. And yeah, so this galaxy came, but it seems that to have been the largest from everything that came to and merge with us.
Okay. Okay, thank you. So, Professor Jorge, you can ask your question.
Oi, Cristina.
Hola.
From all this different research that you have been doing, yeah. Could you tell us what is the relation, if any, between the bulge and the thick disk?
Yeah. So this is a good question. So this is, we are going to enter in more detail of this in the third paper that we are preparing right now. So is the bulge exactly like the thick disk chemically? This is discussed also in the review of with Beatriz, and there are some difference in chemistry, it seems, for some elements. Here, what we see in the data of Anna, that Anna made the paper, is that when you open this box of the bulge into orbital parameters, you see clearly thick disk-like stars there, but you also see a component that is not thick disk, that we think we are seeing a piece of spheroidal that is there inside. And you also see a component of the thin disk very much chemical, very rich, and that you see that part of this very inner thin disk became part of the bar. So the bar has a component that's very metal rich. It arrives, the metallicity there arrives to 0.2 dex, and no 0.5 dex. So if you see those very metal-rich stars, now you know where they could come from. They come from those inner regions, because there you achieve those metallicity. And there you see always this thick disk also there. You see, now we are investigating the thick disk there has exactly the same properties as the thick disk here, which is also what this data enabled you to have a look. So I think the galaxy had a very early on thick disk, which formed almost together with a small bulge, and this is what you see also in some simulations.
Obrigado.
De nada. Obrigada pela pergunta.
Okay, anybody else had a question, a comment? If you prefer, you can also make your question in Portuguese, if you're more comfortable.
É verdade, gente. Podemos falar agora português.
I have a question.
Okay, Roberto.
No, if Beth was before me, no problem.
It's...
Roberto, it's okay. Go ahead.
And then Beth.
I have a quick question. Cristina, but first of all, thank you for your very nice seminar. For a long time, we have been discussing, Oscar Cavicchia, that was my student, Walter Maciel and myself, we have discussed between the border between the bulge and inner disk. Where does this border is? There's lots of arguments, even chemical, dynamical, kinematic. Could you comment about the position of this border? This is an issue sometimes for chemical evolution models. If you put this border, the inner border of the disk, if you put it 1 or 2 kiloparsecs from the center, or 3 maybe.
Yeah, so this is also something we see, and we wrote this in the paper, this Queiroz et al. 2020b, because it's not yet accepted. We see the inner thin disk there out, how can I say, between 2 and 3 kiloparsecs, but in the inner parsec we see more this component of the spheroidal.
Yes.
So it doesn't go there inside.
A single answer for this question.
Yeah, exactly. Yeah. The point is that, do we see a thin disk there? Yeah, we see a metal-rich thin disk there. Okay, but it seems that now part of the data is missing, right? So that's the problem. As you saw, the coverage of apogee is still missing a very inner part. Okay, so we see the inner stars if they have some eccentricity to reach our sample, right? And there, what we see chemically is these more eccentric stars. They are the bar, and because we have really computed the orbits of the stars, and we have made a very interesting plot, which is the probability of a star there be with an orbital shape. And once we have looked to those stars, you see their metallicities, you see it's extending metallicity. So they are not only the metal-rich stars that are on the bar, also the metal-poor stars are on the bar, which suggests the bar is trapping stars. You also have really the metal-poor and the spheroidal component attached to this bar. So that's why it's complex, you see. I think I see a hole. I think I don't see a thin disk that gets to the center. It's more like 3 kiloparsec, from 2 to 3 kiloparsec out. Okay. And you see a bar that is more or less 2 kiloparsec for each side, 4 kiloparsecs for each side. Yeah.
Yeah, this is a complicated problem. Yeah.
Yeah.
Thank you. Obrigado.
De nada.
Obrigado. Beth, you can ask your question.
Oi.
Please go ahead.
Oi, Cris. Como é que você está?
Olá, tudo bem?
So, Cristina, my question was also on this line of Roberto's, in the sense that I would like to inquire you about the inner region, this inner region where within a few hundred parsecs, around the center, where we have this more active region. If you had any information at all on the interaction of this inner bulge region with the bar itself, and also with the bar of stars, and also with this thick, dusty torus or disk that is in the inner region within a few hundred parsecs around the center. So, but in some sense, I think you have already answered.
Yeah, because the 100 parsec, as you see from the, wait, let's go back to this map here. You see here is in kiloparsec. No?
Right.
We still don't have the data here because we have too much of extinction here, right?
Right.
The map is better now with year 17. You can see a bit more. That's why we will push for the interpretations once we have more data. But this is the region here. You see my cursor where you expect to have this encounter of the bar with the thin disk.
Right.
And I think we are seeing this. But to say more things about this very inner region, then it's a different kind of data. There was a very interesting meeting recently on the inner regions, and people who work really in the 100 parsec here with other kinds of data, masers and so on, they can see other things that we cannot. Yeah. And here you see the difficulty. We're trying to we see from the run of Star Horse over the full Gaia data with photometry. We think we see the bar. I show you in the density of the Friedrichs paper, no, in 2019, and now in EDR3 you see the bar in the density. But when you go to the apogee, you lack some lines of sight because of this extinction here, and we think the bar is here. You see, but o cursor. Peraí, gente, o cursor desapareceu. Não sei por quê.
Now it's back.
It's back. Okay. So in this region here, you see that these ellipses show where we think the bar is.
Right.
By looking to the other plot, and also in the paper I didn't discuss here, but when we plot the velocities, we really see the bar. We see the bar exactly here. You see this cross in VR plots, very clear that you see the bar, and then you see also this wave in the disk, because you see in the VZ you see a sort of waving in the disk. That is something that was also seen before, but now you see very, very beautifully.
Right. Okay, great. Thanks, Cristina. Yes, amazing data. And this interaction with the inner region is also very important, because you have this matter accreting to the central, more active region, and there are plenty of stars and maser features, and also compact sources producing very high energy stuff, and it's very interesting. It's a very rich region. So very old stars with binary systems, with the black hole binary systems, and supernova explosions. So supernova ramp.
This is why this is why when we found the young alpha rich stars, we gave also an alternative explanation. Is that if we noticed that those young alpha rich were even more coming from the inner regions and more or less metal poor, and we thought they could be forming here in the region where the bar is the end of the bar, the beginning of the disk, could accumulate some gas, as you see in some maps of gas, and in some simulations, and accumulate some gas that will not participate in the chemical evolution. So the gradients is the gas that are participating in the chemical evolution, as Roberto was just saying. But then you could have a gas that stayed there inert, that was not able to form stars, and then suddenly forms, and then this gas is essentially only alpha, high alpha, and you are forming a young high alpha star. That would be very beautiful, because then it will be forming this stuff, and they will be pushing these stars here, so we would observe them here. This is also a possibility, but the possibility that they are just binary systems that have coalesced mass is also is more simple explanation. But would have been great if it was something coming from this inner region. There's a lot to be done here. That's why I say there is a traffic jam of paper in the bulge, because you can treat the data in the different ways. You can ask the different questions. And what important is to have good distance, good extinction. That's why I said first step, we build something with trust. And we know the caveats. We know our priors. We know the considerations we did to get those results, right? We have, for example, assumed a constant extinction law. The extinction law can vary in the bulge. There are some works showing this, and this would mess up a bit your distance. So all these things, once you work with the data and you are producing the distance and the extinctions yourself, and you know which complementary data use, this gives you much more confidence when you have to push for some interpretation. So we are just starting. Yeah.
Amazing. Congratulations, and yeah, take care.
Thanks.
Thanks, Cristina.
Okay, so let's thanks again, Cristina. Many thanks for.
Can I make a quick comment?
Yes,
Victoria?
sure. Please go ahead.
Just to point out, Cristina, your daughter is on YouTube commenting on this seminar.
Oh, really?
Yeah.
What did she say?
She say she's your daughter.
Okay. I am in a room, she's in another room.
Is a proud daughter. Yeah.
Yeah, it looks like.
Great. Okay, Cristina.
Great, thanks a lot.
Thank you very much. Thank you, everyone.
Bye, Cristina.
Thank
Ciao,
you
Cris.
for those in YouTube.
Thank you, everybody.
Richard.
Ciao Cristina, muito obrigado.
I hope next time I am an IP. I am an
IAG.
Alive.
IAG. Yeah.
Yeah.
Yes.
Tchau, Cris. Fica bem.
Tá bom. Olá, voltamos aqui só por alguns minutinhos para responder uma pergunta do Elielson, que ficou sem resposta. Tô falando em português. So we are back just to answer one last question by Elielson about the fact that if we see some correlation between metallicity and stellar multiplicity in the solar vicinity. So how the binary or the binarity or more stellar multiplicity varies with metallicity is one of the very important questions that we have. The binaries and how they vary with metallicity can also affect some of the results I show you, because we are treating things as if they were single stars. So this is a very important question. I don't have an answer. Specifically, I'm not working with this, but this is just to say that it's a very important topic that we should study. Thanks, Elielson, for the question.